In the early evening of October 4th, 1930, to a cheer from the gathered crowd, the largest airship of its day, the British R-101 cast off from her mooring mast at Cardington to begin her maiden international voyage from London to Karachi, then part of British India. In the early hours of the following morning, R-101 had reached the north of France, but was suffering from bad weather, with high winds and rain hampering her progress. Cruising at over 300 metres, the airship was met with turbulent air. One of the linen panels that covered the ship's hull split open. She dived into the French countryside and burst into flames as the hydrogen that filled the airship ignited. 46 of the 54 on board were killed immediately. 2 more died later in hospital. What was meant to have marked the beginning of an airship network connecting the far-flung reaches of the British Empire now burned in the French countryside, and with it burned Britain's airship ambitions. The British program was cancelled, and scrap metal from the wreckage was sold to the Zeppelin Company, who used it to build another airship, the LZ-129 Hindenburg, an even bigger airship, whose fiery demise heralded the end of hydrogen-filled, rigid-hull airships. However, the replacement for hydrogen, helium, simply doesn't produce the lift necessary for large, commercial, rigid airships. So in order to get off the ground, today's non-rigid blimps sacrifice the aerodynamic performance gained with a rigid hull, and limit it to broadcasting whatever advertising message you like to those watching from the ground. But what if instead of helium, hydrogen was replaced with something even lighter, a vacuum? First, would a vacuum airship theoretically work? An airship floats because of the principle of buoyancy. This is an upwards force exerted by a fluid that opposes the weight of an immersed object. In a body of fluid, pressure increases with depth as a result of the weight of the overlying fluid. So an object immersed in a fluid, such as our atmosphere, will have more pressure exerted on its lower side than its upper side. This net upwards force is buoyancy. If this buoyant force exceeds the downwards gravitational force exerted on the object will float. For example, if the density of a balloon is equal to the surrounding air, it will be neutrally buoyant, just as if it were air. If the density is increased, meaning more mass is in the same volume, the increased mass will result in a larger gravitational force pushing downwards, and the balloon will sink. But if the density is lower, then the reduced mass will mean a reduced gravitational force, and the buoyant force will drive the balloon upwards. A vacuum, you may be unsurprised to hear, has no mass, therefore no downwards gravitational force. It would provide the maximum possible displacement lift, able to lift a mass equivalent to the displaced fluid. For air, that is 1.2 grams per litre. This fact has led many people to suggest building a vacuum airship, including Arthur demise, who petitioned the United States Congress for funding. The House Committee on Ventilation and Acoustics, who, after dealing with their primary jurisdiction, were being useful by considering other issues, recommended providing funding. However, this funding was insufficient to build the craft, and demise withdrew his application. In any case, if built, it wouldn't have flown, as the problem with a vacuum airship isn't its hypothetical buoyancy, but the pressure itself. The pressure that causes an airship to fly can also crush it. Standard atmospheric pressure is just over 100,000 Pascal, the equivalent of almost 6.5 Tesla Model 3s sitting on every square metre of hull. A modern blimp resists this pressure and maintains its shape due to the outward pressure of the lifting gas balancing this force from the atmosphere. But a vacuum airship has no such benefit. It must resist this pressure only through structural integrity. Well, it is possible to construct an object that can withstand these forces. The weight margins on an airship are incredibly tight. The density of hydrogen is just 7% that of air, so in order to be functionally equivalent to the hydrogen-filled airships of the past, the unloaded weight of a vacuum airship cannot be increased by even 20% beyond that of the fabric-covered body of the old airships. This so far hasn't been achieved, and no homogeneous material can even theoretically achieve both the strength and weight requirements. Perhaps, in the future, a composite material can be made light and strong enough to make such an airship possible, but don't hold your breath, because at that point we have replaced an airship filled with a gas that could lead to a devastating explosion with one filled with something that could lead to an equally devastating implosion.